So my talk is actually, it's kind of interface between the data science and Spark and how to what we have been learning here. So it's a very simple example. We'll show that how can we, like when we have written a statistical or a data science application or like a code, how can we actually parallelize in the Spark? So all the techniques we have learned, we just like put inside a code and see that how does it work. So for that, we need a bit of an introduction to what we do, what we are trying to do, as because different people has different backgrounds. So I will choose one of my examples, and one of the things I have been talking a bit, I think like I have given 2 talks already related to these things in UZI, but a lot of people here are new. So this will be more along the direction of what Anthony Tamira was talking on the first day about the approximate Bayesian computation. So I will start from what is basically we do in the statistics and what we try to do, and then go to ABC and one of the examples we show how we are doing with the Spark. So the first thing is that what we do in statistical inference. So in statistical inference, we have a data set. The data set has some observations. We normally say n many observations. So we have y1, y2 to yn observations. And then we assume that the data has been simulated from a model. And then the model is defined with some parameters, theta having d many parameters, theta 1 to theta d. And then we have observed data, which we call y-obs, which will have n many observations and things like that. And then we want to make some statements that we also have some sort of prior knowledge about the theta. That let's say you are talking about, you want to estimate. So one of the examples will be you want to know what is the ratio of man and women in one country. So you want to estimate that. So let's say in that country there is like 20 million people, and you don't want to go, like if you don't have a digital database, then how do you go and sample? Let's say you take 1,000 people, and then you count how many of them is man and how many of them is women, and then take the ratio and you estimate that. So here is the theta is like your parameter of interest, and then you want to make statements about that, as because you took only 1,000 of them, but you originally have 10 million, so how accurately that estimates, and what is the probability connected to that. So how good estimate is that, and what kind of probabilistic credibility intervals you can give. So most of the time the questions are, which value of theta has generated y-obs? So what is the underlying true value of theta? And that's called the estimation, and the main question in the inference. And what is the mean value of theta given y-obs? That can be median, mode, and some kind of questions you can ask. What are the different possible values of theta? And then which interval contains theta 1 with probability 0.95? This is one of the most basic statistical questions. So it's a credibility interval, or what with 95% probability we want to know what would be the probability of theta. So these are type of the questions we want to answer. If you're not familiar with these things, please raise your hands and I can get into the more further details. Yeah. Sure.
So now my question: when you write this y1, is it multidimensional data, or just a set of what is the difference between y and y-obs?
So y is like a general description of a data. So that doesn't have any values in there. So you just like, it's an abstract formulation.
But is it multidimensional data? I don't understand why.
So so y1 to yn means the samples. We have n many samples. So let's say you want to know what is the mean height of people in Switzerland, and you take 100 people. So for each of the 100 person, you have a weight. So here y1 will be the weight of the first person, and y30 will be the 30th person's weight. So that's like the data. And y-obs is one of the structures which you actually observed. So that's the y-obs. Okay. So most of in the statistical theory, we always assume a model, and then we want to work with the model. So there are a lot of different kinds of models. So here we will first introduce the 3 crucial aspects of a model. So the first one is a statistical model. is a family of PDFs. So we describe that given a theta, y was simulated using these models. So here we have an example of the Gaussian distribution. So a lot of you would be familiarized with that. And but in a lot of other problems, the model is unnormalized. That means here, if you notice that this is a PDF function, and the quantity 1 by root over 2 pi sigma square is a normalizing constant. Meaning, if you take an integration of this thing and then divide by the whole PDF function, if you integrate over the whole parameter space, it becomes 1. So then it's a real PDF function. But in a lot of cases, just estimating that normalizing constant is very difficult. That's because you can't do the integration. So there are models where you don't have you don't know the normalizing constant, but you know it's proportional to the PDF function. So as an example will be, let's say in this case you don't know this constant, you can't estimate that. So this is an idea of an unnormalized model. And then the third one, which is much more challenging, where you have no idea of at least in the first and in the second example, you had an analytical form of the PDF, whereas it's an exponential and blah, blah, blah. So you know the mathematical form of the PDF function, and then you can explain, okay, so this is my model, and you work with it. In the second one, I don't have the normalizing constant, but still have a mathematical model. But what is like, you have been told that, oh, there is a model, but I don't know any mathematical equation, but I know how to simulate from that model. Like, if you give me a parameter value, I generate data out of it. So it's virtually a black box or simulator where you have some idea of parameters which affects the data. You plug in the parameters, it churns out the data sets. So this is the kind of problems we call simulator-based generative models, and then it has a lot of applications. So I will come to those. But let's first, so now we have 3 different kinds of model. And depending on what we want to do, so the first one is the likelihood-based inference. So the PDF function you saw, it's also a lot of cases, the likelihood function of the parameter theta. So now PDF of the observed data, when you have the observed data y-obs, is a function of the model parameter L theta. So this thing is called likelihood function. And it captures the information in the data set about the parameter theta you have. So the only thing you have is the y-obs, or the observed data set. And then you want to learn about the parameter from the data set what you have. So everything is captured in the likelihood function L theta, and this is proportional to this thing. So in general, in statistics, until I would say like 1990s also, most of the research were being done handling maximum likelihood estimation or Bayesian inference, where you like function L theta, and then you try to find the maximum value of theta, maximum theta value, which maximizes the L theta. So it's an optimization problem, and that's called maximum likelihood estimation. And in Bayesian inference, you have a distribution over theta, which is proportional to L theta, and the prior information you have. So these are the 2 big paradigms in the statistical inference theory. One is the frequentist, and in the Bayesians, they do it a bit different manner. But both of them assumed that the likelihood function is known. Like it has a mathematical form, and you can do things with that. But if you notice the last slide, here in the first 2 cases, we have a mathematical form of the complete mathematical form, and then it's the unnormalized. So if you have the maximum likelihood estimation or the Bayesian inference, the first 2 things works okay, because you can handle that thing. But when you are in the third situation, when you have a based model, you have a black box. You give theta and it gives you data. Then you don't have any way to do maximum likelihood estimation or Bayesian inference in the traditional manner. So it creates a big problem, as because generally not computable for unnormalized and simulator-based models. It also there is in the unnormalized models. So there have been a lot of research for a long time. In the second one, it's an unnormalized constant is not known. There are works by Besak, Hilton, Huberinian, and Gutaman and Huberinian in recent years. There's a huge area for. But in this In this talk, I will concentrate on the third problem, which is much more difficult, as because you don't have any likelihood function, you have no idea, and that's called the simulator-based models, and we want to see how can we handle that. And we'll talk about one methodology, and then we'll see how can we implement that in Spark. So these kind of things are called likelihood-free inference, as because when you want to infer about the parameter theta without having a likelihood function or without having any knowledge about likelihood function. And why it is so important? Where does it come? So it allows to implement hypothesis of how generated without having to make excessive compromises in the modeling. So if you think about the Gaussian model, so I think like when Gauss proposed it, he was looking into a lot of different histograms coming from the natural science. It's like almost more than 100 years ago. And then all of them looked like bell shape. And then he considered, okay, then like a Gaussian model will be a nice fit, and then he came up with the equation of that. And on the way for last 200 years, there has been a lot of these models people has proposed, and we tried to do statistical inference for them. But in most of those cases, you had a strong assumption that your data actually fits the model you were assuming to. And then we try to model fit and model comparison, which is like really difficult areas. So but when you actually say that I don't have any specific model, I don't have any likelihood function, then that assumption is completely out of the question. So if you consider it as a black box, then the assumption is gone, and you are trying to do inference without that assumption. So it gives you a much more flexibility. Secondly, it's a neat inference with physical or biological models of data, as because in a lot of time the data set is so complicated that defining a model is very difficult. And then the third one is known limits on the number of unobserved variables. Like there can be a lot of auxiliary variables, as because inside the black box a lot of things can happen. You don't really care about them. It can be considered. So in a lot of cases the likelihood function evaluation is difficult, as because there are a lot of latent variables, a lot of auxiliary variables, and then you actually can't integrate them out easily, so you don't have a likelihood function. So inside the black box those things are happening. So until now, is everything clear? Everybody is with me? Okay. So now the basic principle between the likelihood-free inference is that you have an observed data, you have y-ops, and then you take, so there are, okay, let's go through the literature a bit. There are two different kinds of works. One of these approximate Bayesian computation. It was started in around 1998 in population biology. They are the people who first used it, and then came into statistics, and it is majorly used in now statistics around 2012. The paper is there. It's a review paper, but it has been used quite a lot. And in last, I will say 6-7 years, there is an explosion of using these kind of methods. And in 2010 Nature paper, it's another kind of method, synthetic likelihood. It's a bit different, but it takes some other assumptions to do the things. But these are the two streams. But in both of these methods, the main idea is that you take a parameter value theta. So let's say you have the whole parameter space, and you choose one of them, and then you have a black box, and you feed that theta, and the black box will give you a simulated data. And then you have a simulated data, and you have an observed data. And if you compare them, if they are similar in some manner, then you say, oh, maybe that theta is a possible theta, as because it churns out similar data sets. So, and if it is not, then we don't accept it. So that resemblance is we denote here by delta theta if the delta theta is small. Now, what do we do in the ABC algorithms? So ABC algorithms are iterative. So how do we do the optimum algorithm? It's a different question. There are a lot of works. I will not go there, but I'll just show how the delta theta works and choice of some delta thetas. So ABC algorithms are iterative. The basic steps at each iteration are like propose a parameter theta, and from that theta simulate a y theta with the black box, and then we accept or reject the proposal theta, comparison of y theta and x. So how to actually measure the discrepancy between the observed, like this delta theta, it's challenging. It's because you can see that, let's say you have a network, and you simulate another network which is really big and you want to compare what's similar. How do you just measure a distance between them? There are like, yeah, this. Yeah, okay. So there are like there are features from the networks you can extract and then compute distances between those features. And then in some cases you have a time series data set. Like we also work with like weather modeling. So there you have like 40 time series. That's the data set over huge number of time. And then like comparing them, handling them, what would be an optimal way. So those are big challenges we face. Normally we just extract some statistics from them and compute distances between them. So discrepancy measure, like the whole inference scheme here depends on what discrepancy measure you choose and how naturally we have the problem. So there are lots of research going on what discrepancy measure you should choose. Most of the time people do, let's say they're writing a biology paper, they have a specific data set, and they spend 7 months looking for what statistics to choose and what are the distance measure to choose, and then find out the best one gives them the best result, and then they use that distance measure and then statistics. But I suppose that's not very optimal, so we came up with one of the idea of classification accuracy as a distance. So the first thing is that you have 2 data sets and you compute statistics from them, and then so let's go through it step by step. So we assume that sampling from the probabilistic model parameter by theta is easy. As we talked, it's a black box. And then we have sets is size n. So what we do here, so you have one data set here from the simulated data and another is there. So if these 2 data sets are very similar, then you can easily classify them. But if it is you can't classify them easily. And if they are dissimilar, you can easily not classify them. So I will get into an example, then we will see that. So here the examples we are taking is from Gaussian distribution with variance fixed at 1, and we just play with their mean parameter, and we want to see how they are varying. Left panel we have the mean 6 and mean 0. And then we simulated 2 data sets. The black one is our, let's say black one is our observed data set, where the mean was 0. And then we have taken mean 6 and then simulated the these green dots, green data set. And you can see as because they are so dissimilar, you can easily classify them as because you can just create a line, and the classification task is very easy. So the classification will be very high. But on the other hand, if you have a mean half, then here the red dots, they're almost very close to the black dots. So the classification task becomes extremely hard. So you need to improve the classification accuracy, you need to use a very sophisticated classifier. But still, in that case, I suppose, like whatever classifier you say, it will be a coin toss. So this was the main idea we came up with, that okay, so it's like can we classify or can't we classify? If we can classify it well enough, then it's a good method and this is a good distance. Like then they are distant, and otherwise it's not distant. So this is the basic idea of classification accuracy in ABC setup. So bit more going into the example. So we can see like here what we did, that the mean 0 is the true PDF function, and then mean half is the PDF function here in half, and then there is on the PDF function with the green one with mean 6. And you can see like when the mean is varying, then the similar and not, and then this is the plot of the discriminability. You can see the discriminability converges to 0 when it's exactly 0, but then it increases as far as you go. So we have mathematical proofs and things like that in our paper where we show that it's actually a valid distance measure. But let's not get into those things. It's just take it as a nice classification as a distance measure. So what we then do, so we have x and y theta. X was the observed data, and y theta is like we simulated for a theta, and then we create a data set like that, where we pair x1 to xn with zeros and y1 to yn with 1, and then we we choose one of the, then we learn a classification rule, we fix a classification rule and learn the optimal classification rule and find out what would be the classification accuracy between these data sets. And then which is a proportion of the correct assignments, and virtually that's going to be my distance function here. So next one, classification, if you can learn the base classification rule, that will be best, but you can't learn that given a data set, so you need to use cross-pole cross-validation, and you can use something like logistic regression, SVM, which are the popular classification rules. For these examples, we will choose logistic regression, and we will show how we can parallelize it and how does it work. So the next question is now, in this scenario, so we have simulated data sets and we know how to find the parameters which are interesting to us, and we want to make this code faster using Spark. So the main problem what it comes, let's say you have 100 networks as an observed data set, and you want to simulate, given a theta, you want to simulate 100 networks also. And then you want to compare this, like, are these two similar or not? But simulating 100 networks can be very, very slow, as because each simulation takes time. So to parallelize here, you can easily, what you can do that all those 100 simulations for the same theta, you can just parallelize them. Like you can put all the, each of the, like you can take 100 nodes, and in each of them you put one of the simulation, and you simulate a network. And after that, you can just collect them and then compare. So what we were seeing, like learning yesterday, the map and reduce, the virtually you just feed the theta, and then each of the nodes simulate a network, extract the statistics from them, and then combine those, catenate them, and then gives you the whole data set. So that we can do very fast. And so let's say here we have like 500 networks and things like that, and we can do that very fast. But I will not go into a network here. Rather than I will just show with a Gaussian example how does you do the coding. So like these are the things I have been doing with Marcel for like over the summer, a week or so, and we were trying to do these things. So basically, I think like these codes we are already familiar with. Like you first call the Spark context. Here this ABCPy thing, what I have here is a package we have written to do all possible ABC things. It's a Python package. So this thing is actually available in this whole notebook is available. So you can run this code and see how it is run. So all these packages are available there. But I will just explain through it, and then you can just go back and run. There is no exercise for this. So first you create a Python Spark context, and then so this should work. Yeah. Oh, maybe I'm not in the right domain or something. I don't know where am I now. Oh, there is probably something. Oh. Yeah, I already started something. Yeah. Yeah, exactly. Yeah, sorry. Yeah. But I suppose you can just go through it. Like you can, it is nothing. Okay, so then we call different necessary models. As because we are doing ABC, I will explain it a bit more here. So what we need a model. Like where we actually, the black box, we need the black box. So here the black box is the Gaussian distribution, as because we just considering Gaussian example. So here you can put like your model, which simulates the network. So you can just plug it in there, and then we have the prior information, which you take the uniform distribution, and that module we call, and then we also need to extract the statistics from the data. So if you have a network, you can extract different kind of statistics. Here we call the polynomial function. So if you have a data, then if you have x, we consider x square, x cube, and x is for 4, like as our data statistics. And then we consider that as a polynomial. And then we do rejection sampling. So the scheme is rejection. And in this package, when we will release, we are expecting that it will have already lots of different kinds of priors available, a lot of different Gaussian, like lot of different models and different kind of data sets will be available, and of course different MC sampling schemes and different states we get out. Then we need as a distance function. So as a distance function, we have explained that we use classification accuracy as a distance function, and here we use logistic regression as the distance measure. So we call the logistic regression as a distance, and then we import data is a structure of data we use, and then numpy basically. So these are all the modules you need. So, and then we have the modules. We then define what are the values here we have. So here the uniform, we take -0, the lower bound, and then the 5 to 10. So you create for the parameters. So this is for the mean, and this is for the variance, 0 to 10 and 5. So this is the lower bound. This is the lower bound and upper bound of the uniform distribution, and we just create the prior distribution. And the true model defined. So that's we consider it mu equals to 2.1 and sigma is 5.0. And in summary statistics, it's just the polynomial summary statistics extraction. This package is already the smaller version is already available in your virtual machine, so you can go into it and like play with it and see how these things work. So these are the feeding of the summary statistics, feeding of the distance functions, and you simulate y-obs, which has like 10 objects. So just model simulate, you observe, create it, and then you extract the statistics, and it just goes through. So now, where was the spark, and where did we do the spark thing? So that's the part now comes. So we only needed to do the spark inside when we did the MC sampling, like when we go for a theta and we simulate it and extract the statistics and we bring them back together. And all of this thing happening is in the rejection sampling code. So I will go inside the rejection sampling code and have a look into how does this thing work. So this is the code for the rejection sampler. So it takes the statistics function, which was the polynomial we have feed into it, and then the distance was the logistic regression and the spark context. So that's crucial here. We feed these spark context which you already created, and it goes into it. So here what we do here that we sample. So we take one theta, and for that we compute the distance function, and then if the distance is greater than our IPS, and then we continue it. If it is less than IPS, then we accept the theta. So this is the main part where we do the spark. So here first we parallelize, as we saw, it's just like creating ones over different RDDs. So this is the first RDD we create. Is it the one set in all of the nodes? And then we simulate at each of them. So we had like, so how many? It will be n sample. We had n sample of 500. So we'll get 500 nodes, and each of them now has one. Then we consider a map. So the next map will be the simulate function. So we had the simulation function. We put that as the map. So it takes the theta. So we had this theta, and then it just takes the map, and then it creates the next RDD, which is simulated y. So we have 500 y's in 500 different nodes. And then we extract the statistics from each of the y's. So this is another map, and then it creates another RDD. Virtually all like a step-by-step 3 RDDs, and the maps are the simulation and extraction of statistics. And we finally get this StatSim, which has all the simulated, extracted statistics from the simulated data for 500 of them. And then the last step is that collect the distributed data and process sequentially. So here we use the reduce function. Here we have this lambda xy concatenate. So you have 500 the 3 vectors in each of the nodes, and then you want to concatenate them all together. So you will have then 500 cross 5. So you reduce them with this RDD StatSim, and then you finally get the StatSim. So this is the whole part with the spark we do here, like distribute computing each of the nodes by 2 maps, and then finally we just reduce this thing. And then we compute the distance between the sets ops at setsing. And then if it is accepted, then we accept the theta, or not, we don't. And this is a very simple example of what is going on and how to work inside it. And then you can just now call the sampler, which is the rejection sampler, and we have just now I have rank of 10, and then you can plot with MATLAB, and these are the points, but like just 10 is not enough to show it saturates around the true value. You need to plot like thousands, and then you will get the posterior distribution for around the true value, and it will give you a nice idea. But that's virtually what we did, the classifier ABC and then plugging in Spark inside it. So if you have any question, I can probably explain it. And then you can run through all of these codes and see how they work and go play yourself. Okay.
Okay, so now we will go back to analyzing feature data for this notebook on Spark GraphX. I would like to say a few words about graph computation used for research in social networks, and also for the library Spark offers for building and processing graphs. I'm sure you are familiar with the concept of a graph. So we need a list of nodes, which are also called vertices, and then the relationships between pairs of vertices are denoted by edges in the graph, right? And there are many types of graphs that we can build based on the relationships between the nodes. For example, if we model Facebook as a social graph, then we have directional links between the vertices. So it's a directional graph, because if you are friends with someone on Facebook, then that someone is friends with you also. So it's a symmetric relationship. Whereas for Twitter, we have directional or a directed graph, because of the followers property that Twitter provides. So if you follow someone, it doesn't necessarily mean that someone is following you, right? We all follow celebrities or famous people that are interesting for us, but it doesn't mean they follow us back. And there are many kinds of graphs that can be built on Twitter data. In this notebook, we consider the retweet graph. So this means we look at retweets in the Twitter data. We will be using the same data set as before, so the 1 hour on the 24th of June, containing data regarding the Brexit results. And so we will be looking at retweet actions, meaning that if a user retweets another user, then we can create a link between these two users. In the graph, this means the users will be the vertices, and the edge will be the retweet action between them, right? The connection between them. So Spark provides a library for building and analyzing graphs. It's called GraphX, and for the moment it's only available for Scala. It's not available for Python, so this notebook will be again in Scala. And besides a lot of methods for creating graphs, Spark integrates a lot of already implemented algorithms like PageRank, connected components, label propagation, triangle counts, and so on. In this notebook, we will see the first two, so PageRank and connected components. So first, let's have a quick overview of the notebook. So we start again by importing the libraries we need for GraphX. We will be building upon the previous Twitter data set that we used for the previous notebook. So we have to extract from this data set, we have to extract the list of nodes, the vertices, and the list of edges, right? In order to define our graph. So we will be using SQL again for this. right. So once we have selected screen names for the users and the users that are retweeting, we can build the graph by calling one of the methods that Spark provides for this. And we are using here the edge list fire method, which is a method that allows us to build a graph by specifying the list of edges. So an edge is a relationship between two vertices, and the format required for this method is simply by specifying each edge on a single line, and the vertices that this edge connects are specified by the IDs of the users, and we have to format it with a blank with a space between the two identifiers. And we will do some basic stuff on the graph. First, we will print how many edges, so how many relationships, retweet actions we have in the data set, and also how many nodes we have in the graph. And then we will run two algorithms. So the first one is PageRank. I don't know if you are familiar with the concept of PageRank. It was introduced by Google in 1998, if I'm not wrong. And it was used for ranking web pages in the beginning, and it was defined based on how many pages link to a certain web page. So the rank of a page was defined by the number of pages that were linking to that web page. And it's still being used by Google for displaying search results, because the highest ranked web pages are displayed first when we search for something. So the same principle is already translated to articles, right? So when we publish papers, we have the same. We have the citation mechanism. So PageRank applies there also, and it kind of makes sense to apply PageRank to social networks also. As I mentioned in the previous notebook, so we can use PageRank for defining a metric that would indicate how important the user is in the graph. So the user's influence, the authority of the user in the graph. So running PageRank with Spark is very easy. So we just call the already implemented function, which is called PageRank, and we specify that's the convergence parameter. So PageRank is proceeds in several iterations. At each iteration, it constructs the ranks for the nodes in the graph, and at the current iteration, it compares the ranks to the ones obtained for the previous iteration. And if the ranks haven't changed much, so if the difference is very small, then the algorithm has converged. So we specify this convergence parameter. Here it's not so small, so it can be even smaller, but the smaller we set it, the more iterations PageRank will do, and the longer it will take for us to run this. Yeah, and hopefully, so here we run PageRank, and then based on the data frames we created previously, we can associate the ID of the node and the rank with some screen names. Basically, hopefully we will see some people we might recognize if you are familiar with music at least. Yeah, and then we will also run. I'm not going to scroll because it's very long. We will also run connected components. It's algorithm that basically groups together vertices that are connected to each other in the sense that so a component is a subset of the graph that contains nodes that are connected to each other, and they are not connected to all the other subsets of the graph. So there has to be a path in the graph between any two nodes in a component, and that component is not connected to any other component through any edge. And this could be, this is mostly used in social networks for identifying communities, right, for community detection algorithms in social networks. And because connected components in the end indicate clusters of users that are closely connected to each other but are not connected to other users that are not so similar to them in the end. So we will be running connected components here also, and we will print at the end the results to see what clusters we obtain. Okay, so there are no exercises in this, mainly because it's Scala, and I didn't want to scare anyone. It's Scala. So yeah, so I guess we can start running the notebook from beginning and follow all the explanations and see what results we get. And I'm here if you have any questions. Maybe we can have a short break, quick coffee break before we start, 15 minutes, something like this. And then we can start with the notebook. Any questions at this moment? Or not? Okay. We are still running on the virtual machine. Yeah.